In this video, we start looking at how we evaluate limits analytically. Okay, that's a little bit different so far. We've used tables and graphs to help us determine the value of a limit of some function as x approaches some x value c. And here, what we want to try to do is use some other techniques to help us verify that we can write down these limits, rigorously with paper and pencil. So in this video, we're going to talk about several different things. This is kind of going to be a nice introduction video, and then I'll do another one with some more examples and digging into some more of the techniques and things like that. So main thing today in this video is direct substitution, okay? The second is limit properties. We need some properties to be able to kind of do difficult examples, some other useful theorems, and some examples along the way. Okay, direct substitution, the first, will kind of take the main stage of this video. And we have used a little bit already, kind of without knowing it. It's just some basic limits. We are able to do what we call direct substitute. So for example, something like the limit as x goes to 2 of 3x minus 5. You could use a table or graph, but you can quickly determine that as x approaches 2, there isn't anything scary happening with that function. Right? It's a linear function. When x goes to 2, 3 times 2 is 6 minus 5 is a 1. And that is the value of the limit. We were able to really do what we call direct substitute and plug in that x value. Okay? In general, when we can direct substitute, it looks like this. The limit as x goes to c of f of x is equal to f of c. So the limit is equal to the function value. Okay, this guy right here is the function value at c. And again, I underlined here tables and graphs because you can kind of make these all agree. Not make them all agree, but show that with a table and with a graph that the direct substitution for specific functions does work nicely and make sense. Okay. These well-behaved kind of functions are called continuous at x equals c. Okay, and that idea of continuous is something that we'll define later. But just as a precursor, a heads up, those are called continuous functions when you can take a limit and it's the same as the function value, and a couple other things. I want to start kind of here with a theorem, and what these are kind of building blocks of how we work with direct substitutions. I got to say a few things here first. If we let c and b be real numbers and let n be a positive integer, then what we have are a couple things here. The first is that the limit as x goes to c of b is b. And I want to see that makes some sense. I'm going to draw, jumped ahead a little bit. I want to draw a coordinate axis. The line B is just that horizontal line at the y value of B. So as x approaches C from either side, my function is approaching B. Right? That's all there is to it. It's a constant function. It just is. So the limit of a constant is a constant. Number two, the limit as x goes to C of x is also c. Okay, well, what does x as a function look like? It's a line y equals x, right? So when I look at different c values, here, the function is exactly c at those x values. What I spit in, I get back out, right? So the limit as x goes to c of x is also c. And finally here, the third, the limit as x goes to c of x to the power n is c to the n. And again, these are all building blocks, right? These are going to help us evaluate limits of more complicated functions, right? So basically with x to the n, x, and b, I can pretty much make up any polynomial that you can think of. So where this leads us is another theorem. These are properties of limits, okay? And this kind of expands on that previous theorem. Both of these theorems can be proven rigorously. We're not going to do that here. I just want you to be aware and try to get a hold on these building blocks, so when we work with harder examples, you have an idea of where everything is coming from. So another couple initial steps here. Let n be a positive integer. F and g be functions whose limits are the following. The limit as x goes to c of f of x is L, and the limit as x goes to c of g of x is K. So I've just kind of chosen two generic letters here, and those letters represent the limit of each of those functions respectively as x approaches c. From this, we can gather a couple things. The first is that the limit as x goes to c of b, a constant, times f, is just b times L. This is what we call scalar multiplication. I can take a scalar times a function and take the limit of that, and really the scalar is just that. It scales the limit, okay? So it's just b times L. Not so bad. The next one, the limit as x goes to c of f of x plus or minus g of x. You can probably imagine if I take the sum or difference of two functions and then take their limit, that's really not any different than taking the limit of each one and then adding or subtracting them. This is L plus or minus K. The third, as x goes to c, the limit of f times g is L times K. Okay? And that's basically for a very similar reason, that I can add and subtract the two limits. I can multiply them as well. Okay? I can also divide with number 4 here, f divided by g, but I have to be careful. K cannot be 0 in this case. So there's a little stipulation. I can add and subtract limits, I can multiply, I can divide, but I can't divide by 0. Okay, so as long as k is not 0, we're good to go. And one more, number 5, the limit as x to c goes to c of f of x to the power n is the limit of f, which is L, raised to the power n. Okay? You can memorize these if you like. As we go through some examples, I think you'll start to see these kind of working in the background. There tend to be things that we take for granted, so just be aware of them. We're going to use them kind of throughout. I'll show you how things go here in the next example. I want the limit as x goes to 2 of 4x squared plus 3. And I'm going to basically decompose this limit here. I've got a quadratic, 4x squared plus 3, and I'm going to decompose that using all the properties that we just talked about. Okay? So first things first, I know that I can break that sum apart and look at the limit of each one. So what I'm going to do is take the limit as x goes to 2 of 4x squared and add that to the limit as x goes to 2 of 3. I can break apart that plus sign and look at those two limits separately. What I've drawn in that yellow mustardy color there are those constants. The limit of a constant's a constant. The first one here, the limit as x goes to 2 of 4x squared, I know that b, that scalar, really just scales the limit. So what I'm allowed to do is move that 4 to the outside of the limit. And then the second limit there, as x goes to 2 of 3, 3 is a constant. We saw from two slides ago that the limit of a constant is a constant. So that should give me a value of 3. Now, went ahead. 4 times the limit as x goes to 2 of x squared. X to the power n, when I send x to 2, that's the same as taking 2 to that power n. So 2 squared is going to give me a 4, times 4 is 16, plus 3, I just keep carrying down. So the limit here should be 19. So what we do a lot of the time is break things apart and look at them piece by piece. And actually kind of what this gives us, if this was a function here, what I've really done is taken the limit as x goes to 2 of that function, and I really just plugged 2 in. I use that direct substitution. Okay? And actually what we're kind of getting at here, like I said before, you can create pretty much any polynomial with the properties we have so far. In fact, direct substitution is valid for polynomials and rational functions. with non-zero denominators. Again, that's a specific bit we have to pay attention to. We can't have 0 in the denominator. Okay? Another example. The limit as x goes to 1 of x squared plus x plus 2 all divided by x plus 1. I've got a rational function here. As long as the denominator, x plus 1, is not 0 when x is 1, I can direct substitute. Okay? That's it. So what I do is I take my function, and since when x is 1, the denominator is not 0, I can just plug in 1 everywhere. And I end up with 2. These are the questions we hope for, right? Of course, the interesting x value, where I would probably ask you to take the limit of this function as x approaches not 1, but likely minus 1. That's a bit more interesting. But in general, we can direct substitute as long as really what we've got is an x value that's in the domain. Let's do another example. The limit as x goes to 0 of x squared plus 4 is, of course, 0 squared plus 4 should be 4. And another limit, say as x goes to 4, of the square root of x should be 2. We didn't really talk too much about the square root. As long as that c is in the domain of the square root function there, we're good to go. What about the limit as x goes to 0 of the square root of x squared plus 4? So I've kind of combined these functions together. What I've got is called a composition. Okay? So what we say is since square root of x can be evaluated at 4, we can evaluate this composition. Okay? Basically, all we need to be worried about is that when I evaluate kind of a function inside another function, that I'm not violating any domain issues. Okay? So what I've got is the limit as x goes to 0 of x squared plus 4 is really just square root of 4, which is 2. I try to make things complicated, not on purpose, but it's just so that you kind of pay attention. And when you're working kind of inside a function, you've just got to be a little bit careful. Okay? So, some other things we need to talk about. As long as x equals c is in the domain of the function. As long as x equals c is in the domain of the function we're taking a limit of, we should be able to direct substitute. I say should there just to kind of give myself a little bit of cushion to make sure I'm not lying to you. Okay? Let's take the limit as x goes to 0 of tangent of sine of x. Again, I got a function inside of a function. As long as I can direct substitute that x to be 0 in for sine, and then the result of that I can substitute into tangent, I'm okay. Sine of 0, tangent of 0 is then 0. Sine of 0 is 0. So in then for tangent, I'm plugging in 0, and that's inside the domain of tangent. So I don't have anything to worry about. The limit as x goes to minus 1 of x times e to the minus x. Okay? This is just a slightly different example. I don't really have a function inside of a function too much. I guess you could say that minus x is kind of inside the e to the, what we would normally have as e to the x. As x goes to minus 1, I've got that multiplication property here. I've got x times e to the minus x. When I take that limit, it's just the product of the two limits. I've got minus 1 times e to the minus, a minus 1 should be a plus 1. Okay? So really all that is, and it should be something like minus 1 and not 1 over e. Sorry, I missed a minus sign. That should be e to the minus 1 in the denominator. I've made things confusing. Minus 1 times e to the first is just minus e. Okay? Another one, the limit as x goes to 0 of sine squared of 1 minus e to the x. Interesting. breaking things apart a little bit, that sine squared I should write a little differently. That's the same as sine of 1 minus e to the 0 is 1. But sine squared is the same thing as taking that whole quantity of sine of, that's going to be a 0, and squaring it. So what I end up with is 0 squared, which is 0. What if we can't direct substitute? What if we can't? There's some strategy for that we're going to talk about next, and some different tips and tricks and kind of ways around looking at limits where we can't just plug in c. Okay? Thanks for watching.